Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I am learning quickly, I don't claim any real expertise. Today, we're looking at the 46th Project Euler problem. As always, I will link to Project Euler and my repo in the description. Let's dive in. Problem 46 is Goldbach's other conjecture. It was proposed by Christian Goldbach that every odd composite number can be written as the sum of a prime and twice a square. So 9 is equal to 7, which is a prime, plus 2 times 1 squared, which is 2, so 7 plus 2. And then they go on with other examples. It turns out that the conjecture was false. What is the smallest odd composite that cannot be written as the sum of a prime and twice a square? Okay, so the first thing that I'm going to do is to go look up what a composite number is, because I don't actually know. Wikipedia, there we go. A composite number is a positive integer that can be formed by multiplying two smaller positive integers. Equivalently, it is a positive integer that has at least one other divisor other than 1 and itself. So every positive integer is composite, prime, or the unit 1. So the composite numbers are exactly the numbers that are not prime and not a unit. So every number that isn't prime are the number 1. Cool. That makes things easier. Okay. So now is a great place to pause this and go try the problem out on your own, if that is what you would like to do. Again, I encourage that. Alright, so I assume if you are still watching, you have either tried the problem on your own or won't. So let's dive in. So, copying the problem statement over, make our new little file. And I'm going to copy one of these examples, just so I have it like here. Okay, and then as is usual, copy over these two lines. Okay. So cannot be written as the sum of a prime and twice a square. So in other words, it has to be divisible by any prime number, or subtract any prime number, see if that result is even. If it is, divide by 2. Otherwise, we move on. And see what the square root is. So, I'm not sure me saying it out loud made it clear, but I think I know what we're doing. Let's see. I am going to make a guess. I am going to look only at the first 1,000 numbers first and see how that goes. So, similarly to how I've done things in the past, limit of 1,000. And this time I'm actually going to use a different strategy for primes than I have in the past, because it's a little bit faster. And possibly just a teensy bit. Better to go through the entire list first in this case. So I'm going to make an is prime list. Is prime of 0 is equal to is prime of 1 let's see. I'm just gonna make it true times limit plus 1. Okay, so we have a list of trues. And then we're setting the first two elements to false because we know that 0 and 1 are never prime. And then we're going to say for I in range 2 to limit plus 1. If I end up only using limit in this way, I'm going to just go ahead and add a 1. Okay, so for I in range 2, limit plus 1, and actually instead of this being limit plus 1, I want to make it the square root of that, which we do like that in Python, or at least that is a way to do it. That's the way I know. And for each of these i's, if is prime I, then let's see, what is it? We're going to have a k equal to I times I, and then while k is less than or equal to limit, we're going to set is prime k equal to false. And k plus equal I. So it'll go through and, like, for the number 2 up to 1,000, it'll go through and it'll set all of the even numbers to non-prime, which will mean that they are composite numbers, as we just learned. So then what I want to do is for I in range, length of is prime. And I probably could smash these two together, and I might end up refactoring that way. But for right now, this is the strategy I'm going with. And what we're going to say, if not is prime I, then what we want to do is let's see, I'm going to use num is equal to, or not there yet, so I'm actually going to bring back our primes array. So if I is not prime, then for p in primes, or let me put it this way, yeah, I'll just do this. For p in primes, if p greater than I, break. Actually, I'm going to say found solution is equal to true. How do I want to do this? So basically I'm trying to say, yeah, if p greater than I, then we are going to print I and break. Otherwise, we are going to have num equal to I minus p. And then if num mod 2 equals 0, num equals num divided by 2. And then I also want to do num equals num 0.5. So the way that I'm doing this now, this should print out the first composite number that cannot be written as the sum of a prime and twice a square. So if num mod 1 equals 0, then just break. Because we found out that it can be. Okay, so I'm gonna put here. And actually, for this not is prime part, we actually only care about the odd numbers. So I'm going to say, and I mod 2 does not equal 0. Just to weed those out. So we don't even look at them. So we'll only come in here with odd numbers. Odd composite numbers. And then what we've got is... Let's see. Fails conjecture, let's call it. Yeah. Equals false. And then here okay, so fails conjecture false if we hit this line, then we'll just break, and we know that it does not fail the conjecture. If we hit actually fails conjecture equals null. Can I do this? Yes, null is not defined. That is correct. What is it in Python not? Okay. Fails conjecture equals... I'm just gonna initialize it to 0. And then if we hit here, fails conjecture equals false. Which maybe we don't need that part. Come to think of it, since we're breaking out of the thing. But let's follow through on the train of thought here. So now if I set fails conjecture, or if I say if fails conjecture equals 0, or fails conjecture, then we want to print I and break out of this outer for loop. And I'm trying to think if there's a good like, do we actually need both of these here? I think so, because it is also true that it fails the conjecture if we go through all of these and we don't hit this line. So maybe I should just say passes conjecture equal to false. Delete this line. Change this to true. And then just say here, if not, passes conjecture. Then we print out. So that should work. Let's go ahead and give this a real whirl. Have to type Python first. Okay, float object cannot be interpreted as an integer. Feels like that is easy to fix. Yep, that makes sense. Okay. Do you see what we did wrong here? We printed out the number 1, which is the correct answer when you even look at the number 1, which we should not have been doing. So I'm going to go ahead and change that to 2. Run this again. Okay, so now we get the answer 33, which we know is wrong because we have it right here as 31. I am going to go ahead and just do this back at limit plus 1. And see if I get a different answer. I got no answer that time. That seems more legitimate. Let's go ahead and bump it up to 10,000. Okay. And we can see that that ran in, like a tenth of a second. We got 5777. Let's see if this is the correct answer. There we go. Alright, so again, I think perhaps we could do this somewhat differently. For instance, we could have an else if, I think it's elif? Yeah, it's elif. Okay. And then we eliminate the need to go through our data set twice. So, right now I'm just making it somewhat more efficient. Or at the very least, not having to have 2 for loops here. So we go through, look at the range 2 to limit plus 1, which is going to end up being I will equal limit at some point, but that's fine because its prime is that long. If it is a prime number, then we go through and we effectively cross out of being prime all of the numbers that are multiples of that prime number, all the way up to the limit, which, again, I've kind of arbitrarily set as 10,000. If it is not labeled as prime, but it is not an even number, we assume it does not pass the conjecture, and then we go through every single prime. If we get to a prime that is larger than I, we just break. Otherwise, we subtract the prime number. We check whether that leaves us with an even number, and if it does, we divide the number by 2. And then we find the square root. I think I could do all of this in one line, but, like, why? And honestly, I could probably skip this check entirely because I have this one here. But, I don't want to leave even the possibility somehow managing to find the square root of an integer for something that ends in 0.5. Although, I guess maybe that counts. But in any case, num divided by 1, this is just a check to make sure that it is an even integer, like a whole number. And then if we find ourselves in that situation, that means that this number passed this conjecture. So we set pass this conjecture to true, and then we come and we break out of the loop because we proved it's fine. If we haven't set that variable to true, we print out our answer and break out of the loop because we are done. So now it should run even a little bit faster, I would say. Yeah. Okay, about the same, but we got the same answer, so we know that we did it correctly. And yeah, once again, showing that this is the correct answer. I'm going to go ahead and call it there for today, and I'll see you in the next one.